All right, so let's talk about some applications of exponentials. So here's another way that you can rewrite it. So b here, so remember we were writing our function, exponential function, as a b to the x. Now here b is what we call the growth factor. So the factor at which this is growing. But sometimes what they do is that you can get the growth rate, which is the rate at which something is growing, which is very different than the growth factor. Okay, so R here is what we call the growth rate. And it can also be the decay rate. Okay, so what we can do is we can rewrite this B as 1 plus R. Okay, or we can write, if it's growth, or we can write it as 1 minus R if it's decay. If something is decaying, that's what it would look like. So here we can kind of rewrite it as a1 plus r to the power of t and a1 minus r to the power of t. So if you've ever taken finance or accounting, you probably have seen these formulas before for present value or how much money you will get after the first year, given a certain APR. So we can use these two different formulas. Sometimes the growth factor, sometimes it's given to you, like if it's doubled or whatnot, but sometimes they give you the rate itself, the percentage, okay? So we would rewrite this with the growth factor formula. So we would use these two different formulas. So the 1 plus r will be the growth, the exponential growth. The exponential decay will be 1 minus r. All right. So now a here, this number in front of it, will be the initial amount before growth or decay. So let's just do a couple of examples so you guys can kind of see it. So let's say we have the population of a small town in 2016 was estimated to be 35,000 people with a growth rate of 2.4% annually. So find a function that models the future growth. Okay, so we're looking at the exponential growth. So now people aren't dying, they're just growing in this case. So we're going to be using this formula. Notice that now there's no x, there's now a t. So we're substituting it because t stands for time. So it's better to use t as opposed to x. So we're going to write f of t is going to be equal to a1 plus r to the power of t. So now we know initially, so let's take a look at it. So we know initially this is how many people we have. We have 35,000 people in 2016. So I'm going to set 2016 to be our initial amount. This is how many we have in the very beginning. So that means our A in this case is going to be this 35,000. Now we have 1 plus R. So R in this case is telling me the rate at which this guy is growing. So this guy, we need to be very careful because every percentage we always want to convert it to a decimal. So this guy as a decimal will be 0.024. So that's what R is going to be, 0.024 raised to the power of t. So this will be 35,000 times 1.024 to the power of t. So notice here that this is going to give me how many people will be at a particular time. Okay, because this is also including, that's what that 1 is doing, is adding that extra amount. It's adding that 35,000. Okay, because if you didn't have that, it wouldn't quite give you what exactly you wanted. Okay, so this kind of tells you everything. So remember, there's a difference. This guy right here is the growth rate. This is the rate at which it's growing. This is the factor, the growth factor. So everything will be, so you don't need to add anymore. So you can do it by rate, multiply it by the rate, but then you would have to add it to the initial amount. This guy will already adds everything. It does everything for you. It adds up the initial amount as well. So this would be my answer. So now use this equation to estimate the population in 2022. All right, so remember, we let 2016 be our initial amount at t equals 0. So in 2022, how many years is that? So that would be about 6 years. Okay, so that means in 6 years, how many people do I have? So all we're going to do is plug in 6 in here. So f of 6 is equal to 35,000, 1.024 raised to the power of 6. And we want to round to the nearest whole number because it makes sense for people to be whole. we're going to have 35,000, 1.024 to the power of 6. And that's going to give me about 40,300, and I'm going to round up to 53. So that's how many people will be in 2022, approximately. Okay. All right. Now let's look at this particular problem. So the original value of a car is $28,000. So if it is depreciated by 15% each year, find its value in 4 years. So if you've bought a car before, you probably know what depreciation means. So the value of a car every year kind of lowers. So your car, if you bought a car, it's not going to be worth $28,000 every single year. Every single year it loses value. So in this case, the depreciation rate at which it goes down, the value of the car goes down by 15%. So you can see here, this guy's going to be a decay, exponential decay. So let's go ahead and write down our function. F of t is going to be a. Now we're going to use a 1 minus r to the power of t, because this guy is losing value. So a in this case, so it started off as $28,000. And I'm going to do 1 minus the percentage, which is 0.15 to the power of t. So this is going to be $28,000. 1 minus 0.15 is going to be 0.85 to the power of t. And this means exponential decay. You can see that b in this case is a number between 0 and 1, so it's actually going downward. Now we want to find the value in 4 years. So we're going to go ahead and plug in the value of 4. F of 4 is equal to 28,000, 0.85 to the power of 4. So 28,000, 0.85 to the power of 4. That's going to give me about $14,616.18. So in 4 years, your car is now worth about half of what it was worth when you bought it. Okay? All right. So now let's take a look at these next things. So there's going to be some problems that sometimes there's not a fixed rate at which something is growing or depreciating. Sometimes it's growing continuously. And usually these types of problems can be like bacteria, for example. So bacteria, they tend to grow not at a particular rate. They tend to just grow and grow and grow. And that's usually what we call exponential or continuous growth. So when something is continuous, right, then the rate is no longer constant, and we can't use the other two. So how would we go ahead and model something like that? So I'll go ahead and do that in the next video so that you guys can see our new exponential number e and how that kind of works.